Okay, so let's go ahead and get started. So today, what I'm planning on doing is just wrapping up a few final issues in quantum electrodynamics. So essentially, all I want to do today is work out a few more examples of scattering amplitudes in quantum electrodynamics and describe some of the more important, scattering amplitudes which one computes in QED. And that really will bring us to the end of what we're going to be considering this semester. And then just as sort of a final teaser, I thought I would spend the last half an hour of class or so starting to discuss renormalization and kind of giving you a sort of preview of some of the things that we'll be attacking next semester. Okay. So let me just remind you of the Feynman rules in quantum electrodynamics. So last week, we started calculating some diagrams in quantum electrodynamics. You'll be doing some more for your problem set this week. And today I thought I would just spend the next half an hour or so just working out a couple more examples so that you can kind of really get a feel for how to do these computations in QED. So just as a reminder, in quantum electrodynamics, the Feynman rules give you a propagator for a fermion, okay, along with a propagator for the gauge field, which is gauge dependent, and we'll just typically use Feynman gauge, along with, finally, an interaction vertex that allows the photon to interact with the electron. And this interaction vertex carries both a gauge index, both a pair of spinor indices as well as a vector index. Okay. So, for example, the propagator carries two vector indices. The spinor propagator carries two spinor indices, which are usually left sort of implicit, and the interaction vertex carries two spinor and one vector index. And the only sort of subtlety that one has to keep in mind when one constructs Feynman rules in quantum electrodynamics is that we need to be careful to contract spinor indices along the flow lines of these charge conservation arrows, sort of along the arrows, along the spinor lines. Okay. So starting in particular with a U bar or a V bar, which would come from some sort of outgoing particle, so an outgoing electron in the case of a U bar, or positron in the case of a V bar, and then working your way backwards and ending with a U or a V coming from an incoming electron or positron, respectively. Okay. So, and then, of course, in addition to the U's and V's, which are the polarization vectors of the incoming or outgoing positrons or electrons, we also have epsilons, which are the incoming or outgoing polarizations of any vector fields, okay, of any gauge, of any photons. Okay. So let me do an example, and this is an important example, where all of these various polarizations and sort of spinor structures will be relevant, just so that you have some sort of feeling for how all of this works in practice. So this is the example of Compton scattering. Okay, this is one of the most famous processes in quantum electrodynamics. It's the scattering of a photon off of an electron. So we're going to be working only at tree level to compute this at leading order. And so the sorts of diagrams that will contribute, well, so this would be one of them. So let's say that you have some sort of photon with momentum p1 and an electron with momentum p2. And at the end, your electron has momentum p3, and, sorry, that's a photon line. Your photon has momentum p4. Then this diagram that I've written here would be one possible contribution to this process. So this is what you would typically call an S-channel contribution. And there'll also be a T-channel contribution, which would look something like this. Okay. And if you think about it, there's actually no U-channel contribution because you can't get the various spin arrows to line up correctly to make a U-channel contribution. So these would be the only two contributions at leading order, so at tree level. So let's just go ahead and write these out so that you have some sort of practice in writing these out. So the S-channel guy will have two copies of I times the gauge coupling. Okay. We can forget about that minus sign because we're squaring it. So there'll be some epsilon that tells you the polarization of the photon with momentum p1. That's an incoming photon, so you get an epsilon. And then you get an epsilon star for the outgoing photon with the momentum p4. And then we have the momentum line. So you have some outgoing spinner with momentum p3. So I'll just call its polarization U3. And then you have an interaction vertex right here where it interacts with the guy with momentum, the photon with momentum p4. So the interaction was IE times the gamma matrix. So you'll get a gamma nu that you have to keep. So because this it's an interaction between the guys with momentum p3 and p4. So that new index here matches up with that new index here. And then you have a fermion propagator. So that's p1 plus p2 slash plus m divided by the appropriate denominator. P1 plus P2 being the total momentum of the internal particle. And then similarly, we have another interaction vertex where the photons with momentum, the photon with momentum P1 meets the electron with momentum P2. Okay. So that, for example, is the S-channel guy. And the T-channel guy is going to be very similar. So you'll again get an epsilon 1 mu, epsilon 4 star nu. You'll have a U3 bar. But here we need to contract the indices slightly differently. So you get a gamma mu because the electron with momentum P3 meets the photon with momentum P1. And you get a, let's see, it would be, we could write it in terms of P2 and P4. So it would be P2 slash minus P4 because we usually keep the convention that the momentum flows from left to right, plus m over P2 minus P4 squared minus m squared, then with a gamma nu U2. Okay, so those are the scattering amplitudes. And if you care about the polarizations epsilon and u of the incoming and outgoing photons and electrons, if you know what they are, then you just plug that in and you compute it. Very often, we won't care about polarizations. And so if we don't care about polarizations, then we need to sum over the outgoing polarizations or outgoing spins of the electrons and average over the incoming polarizations and spins. So, for example, we would be computing something like the sum over all spins and polarizations of the sum of these two guys squared, these two amplitudes squared. Okay. So that's going to be a long and rather involved computation, and I don't think we want to go through the details of computing each term explicitly, but just so that you get an idea of how the computation goes, if you need to do it yourself, let me just compute one of the terms. Okay, so let's just do the t-channel guy squared, say. Okay. There would also be an s-channel guy squared, as well as, mt star ms times ms star mt. So what would this look like? So you'll get an e to the fourth, and I'll pull out that denominator there, which is t minus m squared, where t is p2 minus p4 squared. And then you have the sum over all values of epsilon 1, epsilon 4, u3, and u2 of, let's just copy down that formula for mt. You get an epsilon 1 mu, epsilon 4 nu star, u3 bar, gamma mu. We can forget about that factor of I, and then we get a p2 slash minus p4, sorry, there's a slash there, plus m, then a gamma nu, then a u2, and then we have the complex conjugate. Okay. And as we discussed last time, when you get the complex conjugate, all you do is you reverse the order of the spinor products, and you change your u2s into u2 bars and your u3 bar into a u3. Okay. So you'll get, so that's mt, and the complex conjugate is u2 bar, gamma nu. Well, let's just be careful. We don't want to recycle our indices. So I'll call that gamma alpha, and then you have a p2 slash minus p4 slash plus m, and then a gamma beta, and u3, and that's contracted with epsilon 1. We need to be careful now. The alpha index is going to be contracted with epsilon 4, and the beta index is going to be contracted with epsilon 1. Okay. And I have to complex conjugate those epsilons because I'm calculating MT complex conjugate. Okay. So now when we do the spinor sums, we can use the fact that the sum over all spins, say, of u2 bar u2 is equal to p slash plus m. And similarly, we can use the fact that the sum over all polarizations of epsilon 1 mu, epsilon 1 alpha star is equal to g mu alpha. Or is there a minus sign there? I believe there's a minus sign there. Right? It's not going to matter, of course, because there are two of them, so those minus signs will cancel. We can then use this to go ahead and simplify this expression. So in particular, so any questions on this so far? So this is the sort of manipulation that you're going to have to get used to. We're not going to do a ton of these manipulations, but at several points we're going to need to go between scattering amplitudes to actual cross sections where these sort of manipulations are important. So when you calculate this sum, pulling out that e squared over t to the fourth, so again, what we want to do is write this as a trace. Okay, so I've written mt squared as, if you think about it, so in terms of spinors, this has no spinor indices, and this has no spinor indices. But what I'd really like to do is move this u3 bar over here to sit next to that u3 here. Okay. Sorry, actually, I forgot. It's u2 times u2 bar, of course. And so in order to do that, I write the product of those two numbers as the trace of a matrix times a matrix, and it's the matrix where that U3 has moved all the way over to sit over here. And then I use these two expressions, so I use this guy here for all of my sums over spins, and this guy here for my sums over polarizations. And what do you get? Well, you get the trace. So first, coming from the U3s, you have the sum over U3 times U3 bar is a P3 slash plus M. And then you get a gamma mu, a P2 slash minus P4 plus M, a gamma nu, and then the sum over U2s is a P2 slash plus M. And then you get a gamma alpha. But remember, we are summing also over epsilon 1 mu epsilon 1 beta to get a G mu beta, and an epsilon 4 nu epsilon 4 alpha to get a G nu alpha. So that alpha is actually a nu, so we get a gamma nu, P2 slash minus P4 slash plus M, and that gamma beta becomes a gamma mu, and then that U3 we've already used that one over here. So that's your expression. And now we can simplify this a bit more. So in principle, this is the trace of a product of 1, 2, 3, 4, 5, 6, 7, 8 different gamma matrices. Okay. So that's something that's sort of hard to compute. So last time we introduced formulas for traces of up to products of 4 gamma matrices. It's completely straightforward, although incredibly tedious to figure out 6, 8, and so forth gamma matrices. But fortunately, a lot of these gamma matrices are contracted with one another. So on one of your problem sets, you actually proved a formula like this. Did I have you prove that formula? Okay. So we can now use that formula that you proved. Okay. And you also proved a formula like this. That's easy. That just immediately follows from the Clifford algebra. So you can use that to simplify this expression. Okay. So for example, you can contract this gamma mu with that gamma mu by moving it through this expression here. And so for that P3 slash, you just get a factor of -2. That's that -2 here. And for that M, that picks up a factor of 4. That's this factor of 4 here. So you get -2 P3 slash plus M, P2 slash minus P4 slash plus M. The gamma nu here can be contracted with this gamma nu here with the similar introductions of factors of -2 and 4. And you're left with an expression which is a trace of only 0, 1, 2, 3, or 4 gamma matrices. The trace of 1 gamma matrix or 3 gamma matrices is equal to 0. We showed that last time. The trace of 0, 2, and 4 gamma matrices is something that we wrote down completely explicitly. And so you can then just plug in these formulas and you get a completely explicit formula for this scattering cross-section in terms of the dot products of these various momenta, P1, P2, P3, and P4. Okay. So I don't want to write down all of the terms. It gets a little bit tedious. But for example, there are various terms. So remember that the trace of gamma mu, gamma nu, gamma alpha, gamma beta has terms like G mu nu, G alpha beta, plus G mu alpha, G nu beta, plus G mu beta, G nu alpha. And so that leads to various terms. So I'll just write down a couple of them. So for example, there's one term where you get a P3 dotted into this vector here. So let's call that vector Q. So let's call Q P2 minus P4. So you'll get terms that look like P3 dot Q times P2 dot Q. and terms that look like P2 dot P3 times Q squared, plus various terms that involve contractions of only 2 momenta instead of 4, with numerical coefficients that you could go ahead and compute. Okay. And this was just one contribution. This was mt squared. And of course, you would need to compute the other contributions and sum them all up to get the full cross-section for Compton scattering. Okay. And the answer that you get is a little bit complicated, but at this point, you could just go ahead and write it down. It's just a straightforward calculation. And I think it's fair to say that this result for Compton scattering is really one of the touchstones of the theory of quantum electrodynamics. So, among other things, it allows you, for example, to compute the dependence of the scattering of light off of an electron or a proton on the scattering angle. Okay. So this is one of the famous computations in quantum field theory. Okay. Maybe I'll just write down the answer for you, because I don't think it's particularly illuminating to go through all of the details. And because it's not particularly illuminating, I didn't actually go through all of it. It's kind of a little bit, the algebra is a little bit messy. But let's just work through one particular case. So let's just consider the following example. So let's consider the case of a photon scattering off of an electron or proton, which is at rest. Okay. So this is one of those famous, I don't know, did you do Compton scattering in your modern physics class? I probably taught some of you in modern physics, in which case you probably did do Compton scattering. So let me just remind you how this goes. So let's just work in the frame where the electron is at rest. Okay. So I think I called the electron's momentum P1. Is that right? I don't remember what I did. I guess I called it P2. Okay. P2 or P3. So P2 is the electron, so it'll be at rest. Okay. The momentum of the incoming photon. So let's just say it's coming in from the z direction with frequency omega. So P3 was the outgoing momentum of the, here, let's write it over here. P3 is the outgoing form momentum of the photon. So let's say it comes out with a frequency omega prime and at a relative angle theta, say in the xz plane. And then P4 is whatever it has to be by the conservation of energy momentum. So it's P1 plus P2 minus P4. Okay. So first of all, you can already conclude. Is there a question? Yes.
P4 is the outgoing.
Oh, I'm sorry. Is that right? P4 is the outgoing photon. Right. Good.
Also, you might want to square the T minus M's.
I might want to square the T minus M's in my denominator. I might. Thank you. Good. Any other typos? They're not typos. I'm not typing. Any other mistakes? Okay, good. Okay, so what can we learn about this process? So Compton, actually I think it was Compton, initially observed that just using kinematics, just using special relativity, you can already learn some things about this process. So, for example, if we use the fact that the final electron state is on shell, so that P3 squared is equal to M squared. So what is that? That's P1 squared plus P2 squared plus P4 squared plus
P1 to P1 dot P2 plus 2 P1 dot, minus 2 P1 dot P4 minus 2 P2 dot P4. Well, P1 squared is equal to 0, P4 squared is equal to 0, P2 squared is equal to m squared. So that tells you that the other three terms, all of those dot products, so that's P1 dot P4 plus P2 dot P4 minus P1 dot P2, those all have to sum to 0. So you can then just go ahead and write those out in the rest frame. What do they look like? Well, the first term is omega prime times 1 minus cosine theta. The second term is m omega prime. P2 to P4. And the third term is m omega. So you can then use that to go ahead and solve for omega prime in terms of omega and theta. So let's see, that's omega prime is omega over 1 plus omega over m times 1 minus cosine theta. Okay. Or, if you want to write this in terms of the wavelength of the final particle, or in terms of the wavelength of the initial particle, this says that, or the final photon in terms of the initial photon, so wavelength is 1 over frequency. This tells you that if you have the scattering of a photon off of an electron in the rest frame, the frequency of the photon will change by an amount that depends on the scattering angle. So this is one of those famous results in special relativity. Just the conservation of energy and momentum in special relativity tells us that if you have an electron at rest and you scatter a photon off of it, I guess photons are squiggly lines, say with some initial wavelength lambda, then the wavelength of the final photon differs from the original photon in a way that is completely determined only by the mass of the electron and the scattering angle. That's just special relativity, yes.
So in that formula there, you have 1 over omega prime minus 1.
Oh, I'm sorry. Yes, thank you. Good. Okay. Yes. Well, as we're working in the rest frame of the electron, and you can't do that as you can't go to a rest frame of something moving at the speed of light. So, what the Compton formula doesn't tell you, however, is how the intensity of the light depends on theta. So we've learned how the frequency of the light depends on the scattering angle, but not how the intensity of the scattered light depends on the scattering angle. Okay. And the computation that you need to do is precisely the computation that I didn't do for you earlier because I was too lazy. Okay. So all you need to do is so here we just computed one part of it. We computed the T-channel part of the process. You also need to calculate the S-channel, and you need to sum over the various polarizations, including the cross terms. And then you need to include all of the various terms that appear when you calculate a cross-section from a scattering amplitude. Okay. So you compute this from ms and mt above, and then you plug into our formula for the scattering amplitudes. Okay. And you get a differential cross-section. It's sort of traditional to write this in terms of d cosine theta in terms of d theta. That's just an overall factor of sine theta out front. And you get a factor of e to the fourth, which we could also write as the fine structure constant squared. Here I'm just quoting the result for you because I don't want to go through the entire lecture's worth of algebra it would take for me to derive this. And you get some answer which is probably, I don't know if it is, but it may well be the first quantum field theory or quantum electrodynamics result that was derived, I believe, in the late 1920s by Klein and Nishina. So this is one of those signature results in quantum field theory. And it's possible to make contact with all sorts of other bits of physics. For example, in the limit where the electron is very, very massive, okay, or the frequency is very, very small compared to the mass of the electron, then omega prime and omega are very close to one another. So that's something that you can just see from this formula here, that as m goes to 0, omega, the wavelength of the scattered photon, doesn't change very much. And so the formula for the scattering cross-section becomes simpler, and you get a result which is known as Thompson scattering. And I'm writing down these formulas not necessarily because it's important for you to remember the exact details, but just so that you can see that quantum electrodynamics can be used to derive things that are interesting and important and can't be derived in any other way. Okay. Any other questions before I continue? Okay, let me just present one final result in quantum electrodynamics. So again, this is something, it's a reasonably straightforward computation. And indeed, it's a computation that is nearly identical to the one that you'll be doing on the problem set this week, so I'm not going to go into too much detail. It's very similar to the electron-muon scattering that I did last class. In particular, what I'd like to consider is the scattering of an electron off of a proton. Okay. So the Feynman diagram that would contribute to this process is one that we considered last class. Okay. So let's say, for example, that the electron is at the top and the proton is at the bottom. Okay, what are we going to do? Yeah. So the incoming electron has momentum p1, and the incoming proton has momentum p2. And then it's a completely straightforward exercise to go ahead and write down this scattering amplitude. It's nearly identical to the one that we wrote down last class. To then go ahead and perform the sums over spins that reflect the fact that we don't care about the spin of the incoming and outgoing proton or electron. And then to calculate the cross-section. And the result, let's see, should I write this down for you? Have you guys seen, I don't know how exciting it will be, have you guys studied Rutherford scattering maybe in your classical mechanics class or electrodynamics class? Have you seen the formula for the differential cross-section in Rutherford scattering? So the formula that you've probably seen if you studied Rutherford cross-section, Rutherford scattering, says that the probability that, or the cross-section for an electron to scatter off of a proton with angle theta is, well, it's proportional to the electric charge for the fourth power, as you can see, because there are two interaction vertices here. There's some numerical factors that we don't care about too much. Okay. I happen to have them in my notes, so I'll write them down. The result goes like the mass of the electron squared, and then there are some kinematic factors. Okay. Okay. So this is the classical result. So let me just explain some of the terms that are appearing here. Okay, so here we're going to assume that the proton is very, very heavy. So the mass of the proton is much bigger than the mass of the electron. So the proton can begin and end at rest, so that, for example, P2 is equal to P4 just describes a proton at rest, and then you'll have some electron which is incident with some energy E and momentum P and scatters off at some angle theta. Now, of course, I've written things in terms of three variables here, E, P, and theta. Of course, they're not all independent. In 2-to-2 scattering, you only have two independent kinematic variables. And so if you think about it, of course, E and P are related by the usual relativistic dispersion relation. But anyway, the formula that I've written here is just the formula for differential cross-section that you get. So this is, I guess it's probably called the Rutherford formula. So this is the classical scattering formula. So how is this formula derived? This formula is derived just by treating the proton as a point source in electrodynamics with a 1/r Coulomb potential, and then studying how the electron behaves as it moves through this potential, so as it interacts with that potential. Okay. You can calculate how much the electron would be bent. You can calculate this differential cross-section, and you get this answer that I've written here. Okay. And then you could go ahead and compute this Feynman diagram in quantum field theory, sum over the polarizations, the spins, all that stuff, write down the differential cross-section, and then work in this limit that we're describing here where the proton is very massive. And then you could take the non-relativistic limit by letting the velocity, which is, so letting the velocity of the electron be very, very small. Okay. And then what you get, I'll just quote for you the result. So this is the first correction to Rutherford scattering. Which, again, is one of those famous classic results in quantum electrodynamics. Again, it's sort of a slightly nasty computation. So in the problem that I assigned you on your problem set, I didn't have you go through all of this because there's a ton of algebra involved. I think it's worked out in your textbook. I'm not even actually sure because there's only so many of these that you really want to work out. In the example that you're going to work out on your problem set that's due this week, I only have you consider some particular limits. I mean, I think I had you consider the limits where the masses are very small or large or something like that, where you don't actually have to keep track of a million different terms that arise when you calculate the scattering cross-section. Okay, because I'm nothing if not kind and benevolent. But I just want to sort of, you know, even though they're complicated formulas, I just wanted to sort of kind of write them down for you just so that you have some sort of impression for the kinds of things that you now have the ability to compute, should you desire to do so. Okay. So this really wraps up everything that I wanted to say about quantum electrodynamics. So, I mean, I guess, what do you write at the end of a proof? QED? Okay. So this wraps up everything that I wanted to say about quantum electrodynamics. What I wanted to do in the remainder of this class is just sort of give you a very brief hint to some of the issues involved in renormalization. And in doing so, I'm going to clarify a question that has probably been bugging you for most of the semester, involving divergences and Feynman amplitudes and things like that. So that's what I wanted to do for the next half an hour or so. Maybe before I do so, because this is kind of a natural endpoint, I can pause and see if there are any questions. So is all of this, all of this sort of spinor technology and all of the, Clifford algebra business, sums over spins, it can be a little overwhelming at first. So, it's just a matter of getting practice with doing it. So hopefully that's something that you either will have or going to be gotten practice with on your problem set this week. Okay. Yes, questions? So in this calculation, of course, the proton is not a fundamental particle. Okay. So, sorry. So, of course you're going to be making some sort of mistake. So, because of course a proton is a bound state of 3 quarks, so I should really have drawn 3 little lines here, okay? Right? I mean, literally, I should have drawn 3 little lines here and 3 little lines coming out, okay? And if you were studying this process at very high energy, then I would be making a big mistake, okay? So then I would be seeing what's known as the parton structure of the proton. I guess that's because it's made of parts, and so they're called partons. I don't know, actually. Probably that might be it. So you would be making a certain degree of some sort of mistake. But the point is that, and this is kind of the underlying philosophy of quantum field theory that we're really going to explore next semester. The point is that if you're only working at very low energies, then you only need to identify the effective degrees of freedom that are relevant at that energy scale. Okay? You don't need to know about quarks and gluons in order to predict the weather. Okay? Well, you can't really predict the weather, but you don't need to know about quarks and gluons in order to study materials. Okay? You don't need to know, you only need to understand what degrees of freedom are relevant at the scales that you're interested in describing, okay? So that's why, if you're interested in studying the nuclear forces at very low energies, you don't need to know about gluons. You can work in terms of the proton, neutron, pion theory that we introduced when we studied Yukawa theory last week. So, and indeed, that kind of general strategy is one that is really going to be the focus of what we're going to discuss next semester. Okay. So maybe just as a bit of an advertisement. Okay. So the way that we typically proceed in quantum field theory and generally in physics is that you really want to you identify a set of fundamental degrees of freedom that you believe describe some system. You identify the set of symmetries relevant for that system, and then you start writing down all of the possible terms that can describe the physics of that system, consistent with this postulate about the degrees of freedom and what sort of symmetries act on them. Okay. And what the idea of renormalization does, and what the idea of what is known as effective field theory does, is it gives you an organizational scheme that allows you to write down what sort of dynamics is going to be most relevant at low energies. Okay? So the idea being that it gives you a way of characterizing what sort of interactions and what sort of quantum field theories you can use to describe systems at low energy, independent of what you think the sort of fundamental degrees of freedom are. Okay? So if you're studying materials physics, those fundamental degrees of freedom that you might be ignoring are the individual atoms that make up the lattice of some material. If you're studying fundamental particles, then the things you might be ignoring are the quarks, if you want to describe some effective theory of the nucleons. But in any case, what we really want to do is come up with a general strategy for writing down kind of, understanding, what the most general theories are that you can write down consistent with some sort of matter content and set of symmetries. Okay? And that's really, I think when you think about quantum field theory in terms of renormalization, Wilsonian renormalization, that's really what you get. So the strategy of effective field theory is really the strategy of writing down all of the possible terms that you can that are, that are going to be relevant at a particular energy scale and with a particular set of degrees of freedom. Okay. And indeed, what we'll see is that you can classify, that there are ways that you can classify the different sorts of theories that will arise. So for example, when you're studying field theories with a particular set of symmetries, then they fall into sort of universality classes based on how they behave under renormalization. That allows, and then, you can make very general predictions based on only a few sort of principles about sort of what sort of symmetries arise and what sort of universality classes your problems fall in. Okay? And I think that, one of the things that's very interesting is that quantum field theory really historically arose because we were interested in discussing the theory of fundamental particles, where the quantum fields that we are studying are are fundamental degrees of freedom, at least as far as we understand. But all of these real insights into how to construct effective field theories, if you want to describe physics only up to a particular scale of interest, those insights really come from condensed matter physics. And they come from ideas of, you take some material and you sort of coarse grain and you forget about, the atoms that make up the lattice, and you only work in terms of the effective degrees of freedom. So in a case of a material, those might be the phonons. The fields that you're talking about might be the phonons that describe the fluctuations of the lattice. In the case of superconductivity, these might be the charged scalar condensates that arise when electrons pair with one another to form a scalar, or something like that. So, what was the question? I don't remember what the question was. Anyway. Protons are not, the answer is protons are not fundamental. Yes, good. Okay, so that was my little diatribe about renormalization. Maybe by way of just, by way of just giving you a very brief introduction to the subject, I can return to something which I've been scrupulously avoiding this class. Okay. So this semester, I have scrupulously avoided considering Feynman diagrams with loops. Okay. And the reason that I have done this, well, there are two reasons why I've done this. The first is that if you have a perturbative parameter that is small, such as the fine structure constant, then loop corrections are small compared to the leading tree level processes that we're interested in studying. Okay. So, of course, these are generally subleading in a perturbative expansion. However, the other reason that I avoid them is that they're confusing. And the reason why they're confusing is that loop diagrams typically have divergences. Now, you've already encountered this on your problem sets. Okay, there are two separate problems. There's one where I asked you to study vacuum energy in quantum field theory, and you saw that even in a free quantum field theory, the energy of the ground state diverged. But you concluded that that energy was unobservable, and it could be removed just by adding a so-called counter term, which is just a constant to your action, which would be completely unobservable. The second place that you encountered a divergence was when you studied the Casimir effect. So in that case, you again calculated a ground state energy of the electromagnetic field quantized between parallel plate capacitors. And again, you saw that the ground state energy diverged.
And that was unobservable, but its derivative was observable. The reason being that the 0 point, the overall value of an energy is unobservable, but energy differences are observable. Okay? In the case of the Casimir effect, they led to a force. And so generally, it's a fact of life in quantum field theory that when you do calculations, say involving Feynman diagrams, you will often encounter divergences, just like the divergence you encountered when you studied the Casimir effect. Okay? But the basic idea that you have to keep in mind is that the only time you ever get a divergence is when you're calculating something that's physically unobservable. And if you phrase your calculation only in terms of physically observable quantities, then you'll never obtain a divergence. Okay? That had better be the case if quantum field theory is to be a predictive theory. Okay? And so what I want to do is just work out for you the basic, simplest example of this phenomenon. Okay? So the simplest example that I can think of is in a scalar field theory with a phi to the fourth interaction. Okay? So let's consider the following theory. So I'm just going to consider a massless theory, just to keep life simple, to make everything extremely simple. Okay? So this is massless phi to the fourth theory. So let's consider the process where you have 2 to 2 scattering. Okay. So the scattering amplitude, at tree level, you have a quartic interaction vertex. Okay. So let's call that term M1. Okay. And M1 is just equal to minus I times the coupling, as usual. And then the next term at one loop level will look like this. Okay. So let's call that IM2. And then, of course, there would be further and further subleading terms at higher order in the expansion in powers of lambda. So let's just go ahead and compute that term and see what it looks like. So let me just make things a little bit more specific. So let's call the momenta P1, P2, P3, and P4. Then, and I'll call these internal momenta K1 and K2. Now remember, the rule that we use when we study Feynman diagrams is you have to enforce momentum conservation at each vertex, so that, for example, K1 plus K2 is equal to P1 plus P2. Okay. So K1 and K2 are not free variables. They're constrained. Their sum is equal to P1 plus P2, and is also equal to P3 plus P4. Okay. That's also just the conservation of total momentum. So that means that, for example, you could let K1 equal to K, and then K2 would have to be equal to P minus K. And the rule that we worked out when we studied, when we developed Feynman rules, is that all of the undetermined momenta need to be integrated over. So we need to integrate over that undetermined momentum K. And what do we integrate? Well, you have two propagators here. You have a 1 over K1. Okay. So there's an I over K1 squared. So I guess I just called that K. And then an I over K2 squared, which is P minus K. So that's the Feynman diagram. And by the way, just as an aside, one of the things that is important to remember is that I could, for example, have used K2 as my integration variable instead of K1. That would just, and if you think about it, if you stare at this expression for a second, you'll quickly see that you would have gotten the exact same answer if you decided to use K2 as your integration variable instead of K1. Okay, you would just get, you would just change the integration measure here, and then you would interchange those two terms. Okay. So what variable you choose as
to parameterize your undetermined momentum isn't actually going to matter at the end of the day. Okay. So let's go ahead and stare at that integral for a second. The first thing that you need to notice when you do this integral is that at very large values of k, so at very large values of the absolute value or the magnitude of k, this integral looks like an integral d4k over k to the fourth. Okay. That's a divergent integral. So, for example, if you integrated d4k over k to the fourth, and let's say you integrated it only over values of k which are less than some cutoff lambda, which we want to take to be very large, then this would diverge, and it would diverge logarithmically in lambda. Is that clear? Okay. Just because the integral dx over x from x going to 1 up to lambda, or 0 up to lambda, diverges like log lambda. Okay. So this is a logarithmically divergent integral, okay, coming from the divergence at large k, which is to say, now large momentum means very small distances. So your first worry is that this expression is going to be dominated by physics at very, very small distances. Okay. So your worry is that in order to predict the weather, you need to know about quarks and gluons. Okay. Because your worry is that in order to make a prediction about very low energy physics, the dominant term is going to come from stuff at very high energy. Okay. So let's, however, go ahead and study this expression in a little bit more detail. So I'm not going to actually do this integral for you explicitly. We'll spend a lot of time doing integrals and learning how to study integrals like this in great detail next semester. So let me just tell you in a little bit more detail what the answer for this integral looks like. So if we have some cutoff lambda that we choose to cut off the integral with, then the answer for the integral, well, it has to be a function of p, and because it's a scalar, sorry, p here being p1 plus p2, because the amplitude is a scalar, it has to be a function of p squared, otherwise known as the Mandelstam variable s. Okay. So if you think about it, lambda has dimensions of energy. So the only way that you can make something dimensionless out of this is if this goes like log s over lambda squared. Sorry, s has dimensions of energy squared. And there has to be a minus sign here, okay? Because this should diverge like log lambda as lambda goes to infinity. Okay. So indeed, one can actually do the computation. This is not something that I'll do for you explicitly right now, but the answer that you get when you do the integral and extract this leading logarithmic divergence, so the amplitude goes like lambda squared, of course, and it goes like a log s over lambda squared. This capital lambda being the cutoff. Now, of course, at the end of the day, we need our answer to be independent of some arbitrarily chosen cutoff scale. That is to say, we need our answer to be independent of whatever we assume about the physics at very short distances or the physics at very high energies. Okay. So how do we do that? Okay. So how is it that this amplitude could be independent of whatever is happening at very high energies, even though it appears to have this divergence? So M2 appears to have a high energy, or what's known as an ultraviolet divergence. But let's think about this expression for M2 here. M2 is UV divergent, but it's written in terms of a coupling lambda, and we haven't been very careful about specifying exactly how it is this coupling lambda is defined. So it appears to be UV divergent when written in terms of the coupling lambda that appears in the action. But what is lambda? Okay, what do we mean when we write down an expression for this coupling lambda? Okay. Well, lambda is supposed to measure the strength of the interaction in the theory. Okay. So it's supposed to measure the strength of the interaction, say, which allows you to, if you send 2 5 particles in and you allow them to scatter off of one another, then lambda is the number that's supposed to measure that strength. Okay. But let's now think practically about how we would define lambda. Okay. If you have some physical system, you don't get to choose the values of the coupling constants in the Lagrangian. You get to, you don't measure the values of the coupling constants in the Lagrangian. You measure the outcomes of physical processes. So what sort of physical process would you perform in order to measure the value of lambda? Okay. Well, one of the processes that you might perform is you might study 2-to-2 scattering. Okay. So if you think about how we would measure lambda, well, if you think about it, one perfectly reasonable definition of what you might mean by lambda is you might define it to be the value of the 2-to-2 scattering amplitude at some particular energy scale. Okay. So one perfectly reasonable thing to do, and indeed the only thing one could do from a practical point of view, is to define lambda in terms of 2-to-2 scattering at your favorite energy scale. So at some fiducial value of the energy. Let's call it S0. Okay. So in particular, let's define the coupling lambda. And so I want to distinguish this coupling lambda from the one that appears in the action. So I'll call it lambda sub r. So this will stand for the renormalized value of lambda. So this is defined in terms of 2-to-2 scattering. Okay. So how would we like to make that definition? Well, we saw that at leading order, lambda is just proportional to m1. Okay. So let me just define the renormalized coupling to be the scattering amplitude at your favorite value of the energy. Let's call it S0. So you could then go ahead and compute this in terms of the coupling constant lambda that appears in the action. Okay. So we have 2 different coupling constants. There's the lambda that appears in the action, and then there's the thing that you would actually observe and call a coupling constant when you perform an experiment. And so if you just go ahead and write down what we got earlier, so M is M1, okay, plus M2. So this would be lambda plus lambda squared over 32 pi squared times this log divergent term. Okay. And then what we would like to do is understand what this apparently divergent term looks like when I go ahead and rewrite it in terms of the physical coupling, the renormalized coupling, instead of the parameter that appears in the action. There's a question. Absolutely. Absolutely. Well, I mean, the question is, what do you mean by lambda? Okay. You can't define what you mean. So if you think about, we don't, when you, we're describing a system of a scalar field and its excitations and this coupling constant lambda. But, when you measure the system, you don't measure the parameter lambda that appears in the action. You never measure it. Okay. What do you actually measure? What you actually measure is something like a scattering amplitude. Okay. So what you actually measure is something like what I call lambda renormalized. Okay. And it's inevitable that you're going to need to choose some sort of process, some energy scale at which to define this lambda. And one of the things we'll see is that all of the coupling constants will need to be defined in terms of physics at a particular scale, and they will change as you change the scale at which you study them. Okay. So, I mean, this is one of the most famous and deepest facts about quantum field theory. Okay. So, for example, this is in the theory of quantum chromodynamics. The reason why nuclear physics is hard to study at low energies is that the relevant coupling constant is of order 1. So Feynman diagram perturbations don't work very well. Feynman diagrams are useless. But the coupling is a function of scale. So if you're interested in studying quantum chromodynamics at very high energies, you actually end up using a different value of the coupling. And at very high energies, it's a small value of the coupling. And so Feynman diagrams are useful. Okay. That's why, actually, it's much easier to make predictions about quantum chromodynamics at high energies than at low energies. Okay. Because at low energies, you need to use other techniques, like lattice field theory or something like that, whereas at high energies, you can just use Feynman diagrams. It's intrinsic to the theory. So for example, yes, absolutely, absolutely. So one of the favorite games, this is the last lecture of the course, so I can wax poetic. One of the favorite games that we like to play in particle physics is you say, well, we've got all these various coupling constants floating around in the standard model. You've got, strong and weak nuclear forces. You've got fine structure constant. They're all different values, okay? But they all change with energy, right? And so you say, what kind of matter content might there be out there that would change the way they flow with energy so that they would all come together and meet at some very high energy scale. Okay. And this is the idea behind grand unification. This is what grand unification is. It's a guess for the sort of matter content that you would need to add to the standard model in order to get these coupling constants to unify. Because it's only if they did that you could view them as, manifestations of, or as limits of some, simpler theory, some more symmetric theory. This is all an advertisement for next semester. I think we may do this. We'll probably do this next semester. Yeah, good. Okay. Good. So let's go ahead and think about what the implications are of this novel way of defining your coupling constant in terms of physical observables. So essentially what we're saying is that the lambda that appears in the Lagrangian is so this is usually known as the Baire coupling. And that is unobservable. Only the renormalized coupling is observable. And so, so here I've written down a formula for the renormalized coupling in terms of the Baire coupling. Okay. And there will be subleading terms coming from higher order Feynman diagrams. And it's straightforward then to go ahead and write ms in terms of the renormalized coupling rather than the bare coupling. So the scattering amplitude, so that's minus lambda squared over 32 pi squared log s naught over lambda squared. So what you then need to do is you need to take this equation up here and invert that to write lambda in terms of lambda renormalized. So that's easy enough to do. So lambda at leading order is equal to lambda renormalized, but there will be a correction term, which is minus lambda renormalized over 32 pi squared log, sorry, there's no s naught over lambda squared, plus dot, dot, dot. So in order to understand why this formula is true, just take this formula and plug it in here, and you'll see that this minus sign here is precisely designed so that if you take this formula and you plug it in up here, you'll just get lambda renormalized is equal to lambda renormalized at leading and quadratic order. So I'm just inverting the relationship up here between lambda renormalized and lambda to get a relationship between lambda and lambda renormalized that'll be good in perturbation theory, order by order in the coupling. So you then plug that into this expression for the scattering amplitude, and you find that the 4-point function at some scale s is related to the 4-point function at our fiducial scale s naught, that is to say, related to the renormalized value of the coupling in exactly the way that you expect. And the loop correction, well, it just tells you not how the theory depends on, the scattering depends on some ultraviolet physics that you don't know anything about, but just the relationship between the coupling at the scale that you're studying and the coupling at the scale at which you defined it. So the important point is that when we write the 4-point function in terms of physical data, rather than parameters in the Lagrangian, which are unobservable parameters, no divergences appear. And this is a general phenomenon. In quantum field theory, whenever you do a computation and you find a divergence, you're computing the wrong thing. If you're scrupulous about computing only physical quantities in terms of other physically observable quantities, you'll never get a divergence. If you do, your theory doesn't make sense. Yes? Yes. Good. Okay. So a non-renormalizable theory is still a theory where if you phrase everything correctly, there are no divergences. It's just a theory with no predictive power. Okay. I mean, this gets back to what I was trying to get at earlier about effective field theories. So essentially, what one can do is classify the theories in terms of, the question is that you're interested in asking is, can you actually make predictions? Okay, and this is what we're going to do next semester, really, is you can divide the world of theories into different categories. And there's some theories which are renormalizable theories, where you can make predictions in terms of only a finite number of coupling constants, things like the values of these lambda renormalized that I wrote down for you earlier. And there are other theories where you actually need, in order to make a prediction, you would need to specify an infinite number of parameters. Okay? These are called non-normalizable theories. So as an effective theory, I mean, I would say that in the last 20 to 30 years, the way that people think about quantum field theory has changed. So if you look at older textbooks on quantum field theory, this is really not the way that they present things. You know, they'll say that non-renormalizable theories don't make sense. And that's really just not true. Non-renormalizable theories are fine as effective theories that are valid up to some energy scale. But what they don't do is allow you to make predictions sort of in a useful way, okay? Because you need to specify an infinite number of parameters as you get up to, some energy scale. Yes. Yes.
But how do you start with the non-perturbative theory?
Well, it depends what you mean by non-perturbative quantum field theory. I mean, yeah.
Here we started to compute the amplitude n,
Mm-hmm.
right, with perturbation theory.
Yes.
And we derive the dependence of the renormalized coupling constant with n.
Yes.
So if we say that this is true in all orders, then it's okay. If we haven't started
Yeah.
using n,
One does. In order for this to make sense, you need to. I'm not sure if this is exactly your question, but you need to make sure that everything I've written down as a ... here is really negligible. And there are places here where I'm being a little too slick for my own good. Okay, right? Because I'm like, if you look, for example, at, I don't know. If you look at this expression, okay, you might think that that second term is supposed to be smaller than the first term. Okay. But there's a sense in which that's not true, because the second term has a log lambda in it, which is infinite. So it's smaller in the sense that it's subleading in lambda, but it's larger in the sense that it's infinite. Okay. And the reason is that lambda is not something that ever makes sense. Okay. So what you should really think of is you should think of, the Baire couplings in the Lagrangian are just things that, they just don't make sense. Okay. They're defined, the Baire couplings in the Lagrangian are defined in terms of the theory where you really have one degree of freedom for every point in space-time. And you should really think of every quantum field theory as built-in having a cutoff. Okay? If you like, the analogy that's useful to keep in mind is that of some sort of lattice. You've got atoms, okay, on a lattice, and you're studying phonons. In that case, the lattice spacing is an actual physical cutoff. There's new physics that appears there. Okay? And that's what the scale lambda represents. The case of, particle physics, if you're studying nuclear physics at low energy, then you might study it up to, the QCD phase transition. Or if you're studying particle physics, your scale might be some high energy scale where you think that new physics appears. Could be the Planck scale. But you should always think of a quantum field theory. There are some cases where you can think of things making sense up to infinitely high energy, but typically you think of a quantum field theory as something that comes with a cutoff scale as part of its, as part of its definition. Renormalizable theories are ones where you can consistently sort of forget about that cutoff scale. Good questions. Okay. Any other questions? Okay, so this is everything that I wanted to say. So let's see. I'll see you on Friday at noon in my office, and you will get an exam. Maybe, okay.
maybe before you go, I can just ask a couple of questions. So this is my chance to ask you about the course. So I've been telling you things all semester. Now you can tell me things. This is the first time I've taught the class, and so when I teach it in the future, I'll probably teach it differently. But feedback that you give me is helpful for me in the future when I teach this course, and it will be helpful for me next semester as I figure out how to approach teaching the course. So maybe, I mean, do you guys have a few minutes? Can I ask questions? Okay. What parts of the so are there parts of the course that you found particularly incomprehensible, needlessly so, as opposed to parts that you found were exactly as incomprehensible as they should have been? I mean, so for example, when I teach this course in the future, I think I might skip the LSZ reduction stuff, the LSZ formula, because it seems to distract a little bit. Or did you like that? You kind of liked it? Okay. Yeah. I mean, the way that I chose, there's many different ways of structuring a quantum field theory course. The way that I chose is kind of the, I don't know, the Peskin and Schroeder way, as opposed to the Coleman or Srednicki way, where I do, the first semester I do basically do tree level stuff. And then the way that some people structure quantum field theory courses is they do everything in scalar field theory. The entire first semester is only scalar field theory, but you do a normalization in the first semester. And then the second semester is spinors and all that stuff. I kind of feel like it's a little, you should see quantum electrodynamics in a first semester quantum field theory course, but I don't know. Do you have any thoughts on that? I mean, you like it this way? What do you guys think about the textbook? I have feelings about the textbook. What are your feelings about the textbook? It does show a lot more steps than Peskin and Schroeder. I mean, what textbooks have you guys actually been using? Have you found most useful? You like Peskin and Schroeder? Yeah. You like them both? Yeah. You like Z? Z is great. Z is interesting. Yeah. Did anyone look at Srednicki or Ryder? Ryder's pretty good. Ryder's pretty good. Yeah. Okay. In Peskin and Schroeder? Yeah. I think the exercises in Schwartz's book are not that great. But do you like Schwartz? It's okay? Yeah. Okay, that's good to know. That's good to know. Yeah. I think in the future I may use Srednicki. I don't like Srednicki because he presents things in an order that I don't like. He doesn't present things in the order that I did it in this class. But he has a lot of details in the derivations, which I think are nice. And the chapters are very short, so it's sort of bite-sized. But he doesn't do as much, I don't know. It's a lot of calculations and not much explanation, if you know what I mean. Schwartz has a fair amount of explanation, which is good. But on the other hand, he doesn't do a lot of things. Like, he doesn't do the LSZ formula. He doesn't do a lot of things that I sort of would want to do. And he uses the wrong signature. And he doesn't contract his indices. Oh my God. I find this so annoying. Yeah. Okay. Any other comments? You can also let me know anything privately. Or you should fill out this course evaluation. You should all fill out this course evaluation thing. But you can also let me know. I mean, what feedback do you have for me about how to teach this course better? Did you like the problem sets? Were they, how many people thought they were not long enough? How many people thought they were too long? Good. Okay. Yeah. Any other feedback from me? Anything you would have liked to see that I didn't do?
I prefer the Blackboard.
Oh yeah, that's a good question. How many people prefer the Blackboard?
It's really useful.
How many people prefer this thing? How many people actually have looked at the video lectures? Most of you. Okay. And also all the people who aren't here probably looked at them. Hello, all of you people listening at home. I know that there's several people in the class who aren't here, who don't come to class, so I know that they enjoy it. Do you guys find the notes useful? I think that in some ways having the written notes is more useful than having the video lectures. I know. But it's hard to, it's a compromise. What I was thinking of doing is next semester actually getting a box so that I can stand up, because it's sort of awkward to sit, because I can't quite see everyone, and I don't know. Maybe I'll try that next semester. Any other so how many people would like? How many of you are taking this class next semester? Oh, okay, most of you. Good. You should all take it next semester. Our ability to offer courses like this in future years depends on the number of people who register, right? So the best way you can show your support, it's like, I guess this is Canada. People don't do public radio advertising, but like, this is like NPR fundraising, The best way you can show your support is by calling your local NPR station and making a donation. Any other feedback for me? Yes. I'll tell you my plan for next semester. Renormalization is the big thing. So it'll probably be, the two things that I really want to do are renormalization, and non-abelian gauge theory, and then as much standard model stuff as I can fit in. So most likely what that's going to be is there'll sort of be old-fashioned renormalization. Then there'll be Wilsonian effective theory. I'm going to try and do some condensed matter examples. I'm going to try and do as many as I can, because that's not something that's usually done. I'm going to see if how much I can do. And then I'm going to do non-abelian gauge theories, which is the standard model, the standard model. And then I'll do as much standard model physics as I can. I'll certainly try and do the Higgs mechanism, probably do some stuff with anomalies. When talking, gravity, so the question about gravity, is a great example of effective field theory. It's a great example of effective field theory. There's a lot of indices to keep track of. So actually computing anything in gravity as a quantum field theory is notoriously index heavy. Having in my real life actually computed gravity loop integrals, I don't recommend it. You may not have a choice. But yeah, so I don't know that, I may certainly talk about it, but we probably won't dive into it. If you look in Tony Z's book, actually, there's a nice section on gravity as an effective field theory. But it's actually not presented very many places. There might be something in Schwartz's book, actually, because he worked on that. Any other comments? So do you prefer, next semester, should I use the tablet? Would you prefer that? Most people would prefer it, yeah. Maybe I'll try and stand up. I don't know. I'll try and see if there's some way. Any other comments for me? Yeah. That would be nice, wouldn't it? What's that? Yeah, maybe, let's put it this way. You could ask Scott. He's the one who gets paid money to do that kind of thing. Not very much money. Yeah, I've thought of, it's a question of time. It's a question of how much time I have for this, and the question of how much time Scott has for this. In the past, I've been able to convince my TAs to write up solutions, but it always takes a little bit of convincing. If you told him how important it was to you and how much it would mean to you to have solutions, he might do it. He's a pushover, so you can probably get him to do that. Yeah. Yeah. There's not going to, with only 10 or 15 people, they're not going to give us 2 TAs. If they did, then yes, I would certainly do that. Okay. Any other comments? Yes.
Small thing, like a very, very small topic, but I think I just didn't understand was, I guess the meaning of a particle as a delta function
in the LSZ reduction, in the LSZ formula? Yeah. That's something that we're going to come back to when we talk about loops, because that's something that's it's kind of not that important when we talk about, well, it is important, but it's more important when you talk about loops. Yeah. I should have spent yeah. I should have yeah. And to some extent, what I'm considering doing is in the future not doing that in this semester and then moving that to next semester. Because
in that case, like when you do loop corrections to the propagator, you can interpret that in terms of the LSZ formula. But on the other hand, it's very important to talk about bound states and resonances, which are particles of the finite lifetime, which you can really understand most precisely in that way. So yeah, maybe I could come up with a good problem set or two on that, because I didn't really think of one this semester. Are there other things that you feel like were not explained well, which I could explain better or differently? I mean, I feel like in the future, this class, I spent a lot of time on the Dirac equation at the beginning of the semester. In the future, I just won't do that at the beginning of the semester and move it to the end when I do the Dirac equation. It was more like, I just didn't know what I didn't know what I was doing, so no, that happens. Yeah. You didn't like the Ward identity? Okay. Well, you didn't understand the Ward. Okay.
And like why it's so, in what way it's so closely related to Ward.
Yeah, Ward identities are pretty important. I mean, yeah, I mean, Ward identities are how you use symmetries in quantum field theory. You know, Ward identities are to quantum field theory as Noether's theorem is to classical mechanics or something like that. Okay. Yeah, anything you tell me now that you don't understand is stuff that I can keep in mind. Anything, yeah. So I can keep this in mind next semester. So we'll have to return to Ward identities, and so I can keep that in mind. Other things that you would like, yeah. Gauge fixing, yeah. I mean, I realized in retrospect that I kind of didn't treat, you know, we did spin 0, spin 1, spin 1/2. I kind of, in each case, I sort of chose my favorite way of deriving the propagator rather than doing it all in the same way. I mean, actually, let me ask a question. I did Schwinger, what is the Schwinger-Dyson equation, and use that to derive Feynman diagrams without using path integrals. My plan in the future is just to use path integrals and not do the Schwinger-Dyson. Would anyone regret that? Do you feel like you would lose something? Maybe, not really. Okay. I mean, it's sort of nice because the way that classical and quantum physics emerges is very clear with the Schwinger-Dyson equation because you can just, the factors of h bar are very clear. But you can also organize things so that it's very clear in perturbation in the Feynman path integral. I mean, the tradition, like the way that Schwartz organizes it, which I don't like, is that he doesn't do the path integral until after he's done QED. Peskin is the same way. I kind of don't like this approach. You're going to have to learn the path integral. It's a great way of thinking about it. You might as well just do it up front. It's a much clearer way of thinking about things. So that's why I kind of structured it the way I did in this class. That's more closer to the Sridnicki or Coleman kind of way of presenting it. You had a comment? No, yeah. No, okay. Any other, did you guys like understand Grassmann path integrals? Yeah? Okay, that's good. Yeah. I guess so. I mean, you know, it's like a graduate class. I could, like, if you basically demonstrate, can I say that? If you basically demonstrate that you've done a reasonable amount of work and, like, have a reasonable understanding, you're going to get an A. Like, it's like a graduate, like, it's not like, you know, I mean, so, I mean, sometimes people, I mean, we could do no exams. Like, I suppose that is a possibility. We could also do like a 1-week final that is just a problem set, but then people get very upset and want to spend all week working on it and get it perfect. And I don't want, like a 24-hour exam, you can get upset, but you're only going to be upset for a short amount of time. So, like that's better. Because I sort of feel like at least, I don't know. I sort of feel like I should do some kind of thing in addition to problem sets. I suppose I don't know. I have to check and see if I could really get away with just not having any exams. That would be nice.
So, for instance, QT last year.
Yeah, what did Kesh, did he have any exam? He didn't even have a take-home exam.
Like, he was planning on having a 1-week-long take-home exam in first semester, but that ended up not happening. He just made the assignments worth everything for the course.
Wow.
needed that second semester, and
Yeah.
Guy's standard model course, he only had assignments.
Okay.
I think he had a final assignment.
Because I don't
also
care,
more.
like, I don't particularly like grading exam. Like, it's not my fun, it's not my idea of a good time, right? I mean, it's sort of nice. The thing that I like is that it's my final chance to get people to learn something. And if I put it on an exam, you're really going to learn it. So it's like, that's why I actually like, because I can come up with cool problems and I'll know that you'll work on them. So that's sort of nice. But I guess I could, I mean, you guys are all doing everyone's like keeping up with the problem sets more or less. So yeah, it's more like I have to do something. Yeah.
I feel like for a graduate level course, people are doing.
Yeah, exactly. I mean, maybe I could do like in the first semester, I could do a take-home exam. In the second semester, I could just do problem sets. That would be fine with me. I don't care. Like, it's more like it's a good, you sort of work hard for an exam and you feel proud of yourself and like stuff you figured out all on your own, and it's a chance, a life-affirming experience, right? It's like reading The Secret or something. Yes.
Maybe give us some focus for presentation.
I just don't think that there's too much. I have to do too much. Like, listen, there's nothing that I would like more than having like 15 lectures worth that I don't have to prepare, and having you give presentations instead. But I just have too much to teach you. I mean, there's just, yeah. Yeah, I mean, a lot of classes do that. But like, if each of you, there's like 10 or 15 people, probably 15 people are registered.
Maybe you expect to get the grade.
Yeah. I just think there's just I just have too much stuff I need to teach for me to give, like, you know what I mean? Like, yeah. Yeah. I would love to teach a class where I just had people give presentations. Boy, would that be nice.
You could just have another class on another
I could just
day
add
just
more.
for
Would people do that? Like, what if I did the following? If we had extra classes in addition to class time where you gave presentations, instead of having like a couple problem sets or something? I mean, it's possible. The thing is that quantum field theory is a vast subject, and at this point, it's like presentations work well when you're at a stage where you kind of are at the cutting edge and you can present. Like, I don't know, like for a standard model class, or for a this quantum field theory and curved space class, or for early universe cosmology. Those are where you're really like, it's appropriate. Here, it's sort of like, you're still learning textbook stuff, and so it doesn't make sense for me to give you to say, oh yeah, give a presentation on chapter 17.1 of the textbook, right? That's just not like, I don't think so. In principle, I think I like the idea of presentations, but for this particular class, I don't think it's necessarily the right thing to do. Yeah. You don't need me to do this. You guys can all get together and have a quantum field theory reading group and then present to each other quantum field theory. That's great. Do it. Yeah, good. Other comments from me? Any other particular things that were unclear? Things that I spent too much time on, too little time on? This is useful for me because, like, I'm the one who has to teach. I have to teach this again, and so the information you give me helps me do this in the future. Problems on the problem set that were particularly terrible or particularly fun? Yeah, that's a good problem. This is this asymptotic series one? Yeah, that's a great problem.
Everything makes sense like around there.
Yeah, that's a good problem. Yeah. Good. Any other comments? You can always let me know at some other point. Okay, well, let's see.